Is that his?
All right, guys.
I think this is
Professor
the
Petta will continue the lecture about semiconductor.
All right, well, thanks for the questions during the last lecture. Feel free to interrupt, make me pause if there's something that's unclear. So I'm going to change gears a little bit for the second lecture and talk about devices that are on some level are quite similar to the last lecture, but we're going to add another degree of complexity. We're going to take our quantum dot devices and build a cavity around them. So this second lecture is mainly going to be focused on light matter interactions and coupling single charges to single photons and heading in the direction of being able to couple single spin to single photons. So here's an outline of the lecture. I'll talk about cavity QED with quantum dots, how we can couple light to matter in our experimental platform. And then the second lecture is really going to talk about non-equilibrium physics. So instead of working at a system, all population in the ground state, we're going to drive our system out of equilibrium and look at the combined interactions of light and matter in these non-equilibrium conditions. I'll talk about photoemission, mazing, and some recent results that show that we can coherently couple a single charge in a quantum dot to a single photon, and some more recent results here showing how we can use these cavity-coupled devices to probe the Valley degree of freedom in silicon. So I want to give credit to the people that largely did the work here, but most of the experiments we're going to talk about were performed by Yinyu Liu. She just graduated a couple of weeks ago and is headed to Harvard to work with Amir Yacobi. And most of her experiments involved indium arsenide nanowire quantum dots. As I mentioned in the past lecture, for reasons of coherence, there's been a transition from 3-5 semiconductors to group 4 materials, things like diamond, NV centers in diamond, silicon quantum dots, graphene quantum dots. And we have a big effort in the group making qubits in silicon, and that's been led by David Zajac and Xiaomi, who are shown here. Okay, so I want to talk about what are called hybrid quantum systems. And these hybrid quantum systems are the result of a marriage between semiconductor quantum dots and superconducting qubits in a large extent. But we're going to take our semiconductor devices, and now we're going to place them inside of high quality factor cavities that we can use to trap microwave frequency photons. And the goal of this physics is to look at interactions between the bosonic degree of freedom, the light that's coupled in the cavity, and the charge degree of freedom that is associated with our quantum dot device. These experiments kind of come in two different flavors. The first flavor is to look at charge-light interactions and charge cavity coupling. This is a figure from Andreas Walras' group showing a gate-defined gallium arsenide quantum dot device that's been placed in a cavity. And really, the questions here are kind of basic. Can we get charge and light to hybridize at the single electron level, in these quantum dot systems? Another thing that we've been looking at in the group is the superconducting qubit community has developed a sort of whole suite of measurement technologies that are really powerful for probing superconducting qubits and measuring single photons. And so we've kind of asked a question, can we use cavity QED in the microwave frequency regime to efficiently read out our charge and spin states? I mean, remember that for the spin measurement, we needed to do a measurement before the spin relaxes, right? For a charge measurement, you need to measure the charge before the charge relaxes. And just remember, students taking all this data and they want to graduate at some point. So having faster ways to take data is always helpful and important. And we really push the limits here. We can now measure a charge state in 400 nanoseconds and kind of take data in a video game mode where you can really feed back and adjust the gates and see how the device responds. That's a charge. And then there's also an open question that I think we'll answer this year is whether or not we can couple a single spin to a single photon. And there's been a large body of work, by several groups looking at coupling spin ensembles to cavity fields. So trying to get spin to talk with light. This is generally done by taking big crystals, containing on the order of 10 to the 10, 10 to the 12 spins. This is a piece of diamond that has nitrogen vacancy centers in it, and coupling these spins to the photonic field of a cavity. What we're really after in my group, and several other groups are also chasing after this as well, is to try to couple a single spin coherently to a single photon. and look at hybridization of spin and light. And there are a few different ideas here. This is a figure from Takis Kantos's group where they've taken a carbon nanotube with magnetic electrodes and kind of pushed in the direction of trying to couple single spins in a nanotube to a single photon. What I want to talk about in this lecture is mainly microwave frequency quantum optics. So what we're going to do is we're going to take our quantum dot device, in this case it's a semiconductor double quantum dot, we're going to trap a single electron in it, and we're going to couple it to a cavity mode, high quality factor cavity that we can trap light in, and the energy of the photons in this cavity is closely matched to transition energies that are associated with our charge states and our double quantum dot. And so really the open questions are, if we take a quantum dot and we drive some kind of charge transition through it, let's say we force an electron to tunnel from the left dot to the right dot, does that transition emit light? Can you actually see photoemission from that? And if we place a system like this inside of a high quality factor cavity, can we see stimulated emission? Can we make a maser, microwave frequency emitter that's driven by single electron transitions in this device? And what do the statistics of the light field look like? There's a way to measure that. Another thing that's important, and we saw this in the previous lecture for that spin T1, right? The spin lifetime was set by electron-phonon coupling plus spin-orbit coupling. And so we know that lattice phonons play an important role in our system. And for these cavity-coupled devices, we can couple charge to light, but the charge is also coupled to phonon degree of freedom. And it's a question of what's the interplay between the electron-phonon coupling and the electron-photon coupling, and can we have sort of higher order processes in our experiment where we relax from the excited state to the ground state by emitting a photon and a phonon through some Phonon Sideband process. And toward the end, I'll show you, it's kind of a cute applied experiment, but can we actually use these cavity-coupled devices as microwave frequency sources, at low temperatures for qubit readout? So let's just talk about the basics. If we wanted to make a laser or a maser in the laboratory, there are three key ingredients that we would need to put together. First thing we need is a gain medium, something that when light passes through it, give us amplification of the light field. And generally we want to place this gain medium inside of a high quality factor cavity so that the light in the cavity will bounce back and forth and travel through this gain medium, and after many round trips through the gain medium, see a lot of amplification. The other thing that's important in terms of the physics of the gain medium is that we need some kind of energy supply, and the purpose of the energy supply is to generate population inversion. We want to place the atoms or molecules in our gain medium in some kind of an excited state. And this excited state population inversion can lead to a stimulated emission process, which is just shown here, in a cartoon picture. So here's a simple picture of stimulated emission. Imagine that we have a two-level atom. It has a ground state energy E1, an excited state energy E2, and we've carefully picked this energy so that it matches the energy of the incoming photon. If we have a way of preparing this two-level atom in the excited state, this incoming photon will interact with it, and there'll be a transition from excited state to ground state, and we'll get two photons out at the end of the day. The one that we sent in, and the one that results from the stimulated emission from the excited state to the ground state. So we need to put all these three things together. And what we've been thinking about in my group is there a way to make a device like this, a laser or a maser, that's driven by single electron tunneling events in a quantum dot device? So the key elements of our quantum dot micromaser are going to be, gain medium. It's going to be a quantum dot. In this case, it's a double quantum dot, two dots that are coupled together. We're going to trap the light in a microwave cavity, a superconducting cavity. And the way that we're going to pump our system and create the population inversion that's required for stimulation emission is we're going to take this double up potential, hook it up to source and drain electrodes, and basically apply a bias voltage across the device so that electrons will tunnel through this double up potential via sequential single electron tunneling. And the question is, can we get light out of one of these tunneling events, right, and pump up the cavity field through these tunneling processes? So our gain medium in these experiments is a double quantum dot. And in the previous lecture, we reviewed the basics of how to make a quantum dot from a two-dimensional electron gas. In these experiments, we're making a double quantum dot starting with a quasi one-dimensional electron gas. It's kind of a different design experimentally, and we're working with these indium arsenide nanowires that are shown here. These nanowires are grown through a process called the vapor-liquid solid growth process. It's a really elegant process. It was developed in the mid-60s and has been used to a large extent, by various chemistry groups. So basically, you take a substrate, in our case, it's indium arsenide. You deposit some gold particles on it, and then put this in a nanowire reactor. And you can flow in reactive gases that contain indium and arsenic, and these gases will supersaturate these catalyst particles and basically plate out atomic layer at a time, indium arsenide layers. And so you end up with a forest of nanowires. This is a cartoon where the diameter of each nanowire is roughly set by the diameter of these gold catalyst particles, and the length of the nanowire is roughly set by the length of your growth time in the reactor. So you can control diameter and length. We try to get the diameter so it's a couple of Fermi wavelengths. It's a quasi 1D channel that we can make our devices out of. And this is a transmission electron microscope image just to give you an idea of what a real nanowire looks like. These are grown downstairs. The diameter is about 50 nanometers. And you can see that they're highly ordered. What we want to do now is make a device, a double quantum dot, out of a single nanowire. And so we pluck one of these nanowires off of this growth substrate, and we lay it down on a silicon substrate that's been patterned with these gold gate electrodes. Can you see these in the image in the back? And so you have your nanowire, and the nanowire is set on top of some metallic gates. And by adjusting the voltages on these gates, we can create a double well confinement potential along the length of the nanowire. That's our semiconductor double quantum dot. In this case, it's made from a 1D wire. To get a current through the device, we put down source and drain contacts, and we can actually have a current flow through this device. And these gates that are underneath it are actually electrically isolated. So there's no current from the gates through the nanowire. These are just depletion gates that are insulated from the nanowire. The last lecture, we talked about Coulomb blockade for a single dot. Let's talk about how that changes when we add another quantum dot to the system. This is a circuit diagram for a double quantum dot. This is the left dot. This is the right dot. Each dot has a charging energy, E squared over 2C associated with it. And we've connected this double dot system to a drain and source electrode. We want to ask ourselves, what's the electrostatics of this system look like? This is a little capacitor that we can charge up, and we have another little capacitor next to it. These capacitors are basically coupled together through some mutual capacitance. And what this means is that the energy of an electron in the left dot is going to be sensitive to the number of electrons on the right dot. There's a mutual Coulomb interaction between these two quantum dots that is going to lead to what's called a mutual charging energy. And so we can plot out something that's referred to as a charge stability diagram. This charge stability diagram is a plot of the electron occupation in the left dot and the electron occupation in the right dot as a function of the right gate voltage and the left gate voltage. And what you can imagine is if we make the right gate voltage more positive, we can pull one electron into the right dot and then a second electron, so on and so forth, and just increase the number of electrons in the right dot. If we change the left gate voltage, that primarily couples to the left dot, and we can add one electron, a second electron, so on and so forth. Question for you is, why doesn't, think about a real device, why doesn't this look like a checkerboard?
I guess it would be a coupling if, it would be a checkerboard if the coupling was 0.
Yeah, that's right. So this gate always couples a little bit to the faraway dot, right? And it's just an experimental matter of life that there's a little bit of capacitive coupling to the faraway dot. And so that gives rise to the slope on these transitions. It tells us why they're not perfectly horizontal and perfectly vertical. What about the splitting there? This little kink tells me that when I add one electron to the right dot, I actually increase the energy of the electron on the left dot. So that's the mutual charging interaction coming about, right? So this little splitting here is due to the fact that the energy of an electron in the left dot depends on how many electrons are actually contained in the right dot. So that's the basic physics of this charge stability diagram. So, why do you care? We can measure this in the lab. These are two voltages that we can set and adjust, experimentally. And by moving around in the stability diagram, we can change the electron occupancy. 1 on the left, 2 on the right, or 0 on the left, 2 on the right, so on and so forth. And so it's a map between voltages and charge occupation. I'll show you how you measure this. There are a couple ways to do it. This is a plot of the absolute value of the current as a function of the right gate voltage and left gate voltage. What we see are pairs of points where the current is non-zero. And these pairs of points are separated by large area where nothing happens, where the current is just zero, basically, to within the resolution that we can measure it. These points correspond to the triple points here. These are called triple points in the charge stability diagram. And the in-between zones where there's no current means that the double dots in Coulomb blockade. And there's a large energy cost that you need to pay to have current. So there's no current flow within these regions. Also, this is done in PowerPoint. The dashed lines are not data. That's just overlaid for clarity. But you can see that there's a honeycomb-shaped kind of unit cell that's repeated out in this two-dimensional space. And that just comes about from the charging physics of this double dot system. So these are some of the signatures of a double quantum dot.
Excuse
Yes?
me, your red circle missing triple points?
Yeah, this is a figure I pulled from one of our papers. And I'm not going to talk about it in this lecture, but there's something called polyblockade, where you can have a spin selection rule if you have an even number of electrons that will prevent current flow because the electrons are in a triplet and you can't have double occupancy of 2 spin-up states. And so what you expect to see for polyblockade is an alternating kind of on-off dependence, and that's what's shown here. But that's spin physics. Yeah, that's a good question. Any other questions? Right. So this is the charging diagram. Let's talk about the cavity. The way that we make our cavity, imagine doing this in an undergraduate physics lab. You take 2 mirrors and you trap light between them, and you just want good, high-quality mirrors so you get a lot of reflections back and forth. Due to the way our devices are made, right, the particle in a box energy spacings are tens of microelectron volts. And therefore, if we make an optical cavity, it's just in the wrong energy regime. It's way too high of energy to have any coupling to a device. So instead of coupling to optical photons, in our experiments, we couple to microwave frequency photons. And the way that we do this is by making a superconducting resonator. And you imagine you take a coax cable, and you get out an X-Acto knife and slice through it. There's a central conductor in a coax cable, and then there's a sheath around it, right? So kind of lay that flat. Here's the central conductor. Here's your ground, and there's ground above it. And now what we want to do is we want to make a resonator out of that transmission line. So you get your knife out again, and you chop here, and these end up being little capacitors. And those 2 capacitors act like the mirrors in this microwave cavity. So I have reflections at those 2 capacitors. And by setting the length of this section between the 2 capacitors, that's basically a lambda over 2 resonator, because I can fit a half wavelength in to that mode. So this creates a superconducting resonator with resonance frequencies that are somewhere between 5 and 10 gigahertz typically, and with quality factors that are on the order, say, 5 or 10,000. It's an optical picture of the device. It's a 1 millimeter scale bar to give you an idea of how big it is. It's a pretty big chip. Why is it so big? The wavelength of microwave frequency radiation is on the order of a centimeter. And so we need to fit a centimeter or so to trap light here. How do we couple this and combine these 2 things, the cavity and the double dot? Well, let's kind of zoom in now. Here's a full picture of our device. I'm going to zoom in with the optical microscope, and now this is a 10 micron scale bar. And what you're looking at here is labeled resonator, but that's basically this central conductor. And now what we're doing is we're going to place our quantum dot inside of this resonator so that we can couple the charge in the quantum dot to the electromagnetic field of the superconducting cavity. Let's zoom in again. This is a 100 nanometer scale bar, and this is a scanning electron microscope image that gives us resolution at these length scales. And here you can see the single indium arsenide nanowire. It's been laid on top of these gate electrodes that we can use to create the confinement potential. And we have our drain and our source electrodes. All right, so now here's the rub, is that we have one electron that we're going to trap in this nanowire. It's localized in like 100 nanometer length scale, and we want it to talk to this cavity that's like a centimeter across. It seems really unlikely it's going to work, right? So there's a little trick that we play. We actually connect this source contact of the nanowire up to the resonator, and we connect the drain of the nanowire to the ground plane of the resonator. And so one way to think of the resonator is like an LC oscillator, right? So I have an inductor and a capacitor, and they resonate, and there's an oscillating voltage. We want to couple that voltage to our quantum dot device. And the way that we're doing that is by directly connecting up our quantum dot device to the two different sides of the capacitor in this LC circuit. Think of it that way. And therefore, this entire voltage that's dropped across this nanowire, it's dropped over about a 500 nanometer length scale. It gives us a really large electric field in the region where our dot sits. And this is important to get the charge to actually talk to the microwave frequency photon. So this is worked out by Carl Peterson, a former postdoc in the group. Now what we can do is we can probe this system by shining light through the cavity. We can take a microwave signal generator, shine light in, and look at the transmitted signal, what comes out the other side. But you also see that when Carl set up this experiment, he has a little inductor that's connected to the cavity. And what that allows us to do is it allows us to apply a DC voltage across this device, and we can measure the current through it. So we can do old-fashioned transport measurements and combine that with microwave frequency spectroscopy to really probe the system in two very different ways. Here's what's surprising. Take light, shine it in, and you look at what comes out the other side. You can measure the amplitude of the signal that exits the cavity, and you can measure the phase of the signal that exits the cavity relative to the light you put in, right? So you put a sine wave in, a sine wave comes out the other side. It has a different amplitude, but it might also be phase shifted by a little bit. So we measure amplitude and phase, and this is the phase shift, plotted as a function of the right gate voltage and the left gate voltage. And if you look at this, you can see that for 99% of the area, nothing happens. The phase shift is 0. But there's a really large phase response here for this line, this diagonal line. And this is a so-called interdot charge transition. It corresponds to one of these transitions in the double quantum dot. And I want to just explain, kind of hand-waving away, why light interacts with the charge in this double up potential at this location in the charge stability diagram. Okay. So here's the picture that you should have in mind for a double dot. It's a double up potential, and I put one electron in it, and I can tilt it this way so that the electrons on the right falls downhill, or I tilt it this way so that the electrons on the left falls downhill in energy. Okay. So if we're far detuned to the left or far detuned to the right, we want to compare two energy scales. One is, what's the charging energy? Well, charging energy is typically millielectron volts. And what's the photon energy at 10 gigahertz? It's about 30 microelectron volts. So I have a few MeV, millielectron volts, and 40 microeV. And so that photon just doesn't have enough energy to kick the electron and do anything. So these are so far out of resonance that there's no light-charge coupling when the system's detuned. So what can we do to compensate for the charging energy? We can change the voltage on these gates and move to this point, somewhere along this line. This is the interdot charge transition. And what's special about this interdot charge transition is that the left dot and right dot charge states are in resonance. We've nulled out this charging energy so that an electron can basically hop back and forth between the left dot and the right dot without having to pay this huge energy cost. And so now we have this microwave voltage. It's just a microvolt or so. A voltage, it's oscillating these energy levels. And if the detuning is 0, that oscillating voltage can cause a charge to hop back and forth on the double dot. And that damps the cavity field. The levels are far detuned like this, and I put on a microwave oscillating voltage. There's not enough energy to drive a transition all the way up, so nothing happens. It's only at sort of 0 detuning that we expect to see a cavity response. So you can, open up Cohen-Tanucci or Griffiths and pull out your favorite two-level system of avoided crossing, and this is basically what you have for a charge qubit. You have a left dot charge state where an electron is in the left dot, its energy increases with this detuning parameter, which is basically a gate voltage. There's a right dot charge state. Its energy goes down with detuning, and charge on the right is coupled to charge on the left by what we call an interdot tunnel coupling, TC. Okay, so that's the off-diagonal term in our Hamiltonian. And to have a nice intuitive picture of why you have coupling, take the second derivative of one of these bands. And what that does is it gives you a quantity chi, the polarizability. Polarizability tells you if you tilt those electron levels by just a little bit, does a charge move or not? And if you're right at zero detuning and you make a small perturbation on the levels, you'll have a large susceptibility. So what this cavity measurement does is it probes the polarizability, basically, of this artificial molecule. And one important question is, how large is that coupling? How large is the electric dipole coupling between this one electron in this double dot and this centimeter-long cavity? And the way that we can measure this is by using what's called input-output theory and the Jaynes-Cummings Hamiltonian. And we can basically map out the phase shift as a function of our interdot barrier height and level detuning and fit these data to extract the electric dipole coupling rate. And in this particular experiment, there's about a 30 megahertz coupling rate between the charge in the double dot and the photon in the cavity. Okay. And this is pretty typical. There are 3 other groups, I would say, working in this field. There's Andreas Walrath's group, Takis Kanto's group in France, and there's a Japanese group that's performing physics in these devices. And all the coupling rates that we've measured are kind of in this range of 10 to 100 megahertz. All right, so we have a gain medium. It's a double dot. We have a cavity. It's a superconducting resonator. These things are electric dipole coupled with this rate of 30 megahertz. Question now is, can we actually get light out of the cavity? So let's talk about the next step, which is how can we pump energy into the system? So what we're going to do now is we're going to take our double dot, left dot and right dot, source and drain, and we're going to hook the source and drain electrodes up to a battery. What the battery does is it changes the chemical potential of the left lead relative to the right lead and opens up what we call a bias window. And if you look at this energy level diagram, you can imagine I grab an electron from this lead, it hops into the right dot, tunnels over to the left dot, and comes out the other side. We can have sequential single electron tunneling through this double dot system as long as these 2 levels are within this bias window, and as long as the level detuning is set such that there's always downhill in energy electron tunneling. Remember, we're at 8 millikelvin. So if I have an uphill tunneling event, current's going to be 0 because I'm just not going to have enough energy to kick the electron up in energy. So it's only within these are called finite bias triangles, where we actually expect to see a current flow through the device. Now, we need to remember that there's this charging energy, E squared over 2c, that we need to pay for electron tunneling. So transport takes place via 1 electron at a time, sequential tunneling events. And therefore, you can think about this current flow microscopically in terms of single electron tunneling events. You start with an empty double dot. We load 1 electron into the right dot. We push that single electron to the left dot and then kick it out of the left dot. That's 1 transport cycle in our device. 1 electron kind of hopping through the device. That's the physical picture of what's going on. And these tunneling events have rates. There's a rate gamma left associated with changing the left electron number. There's a rate gamma right associated with changing the right electron number from 0 to 1. And this tunneling event from 0, 1 to 1, 0 is called an interdot charge transition because the electron's moving from the left dot to the right dot. Is that okay? All right. So here's some background. The physics of this transport process studied a long time ago. This is papers by Fujisawa and Tarucha from the late 90s. And what they did in these experiments is they applied a source drain bias across the double dot, and they measured the current through the double dot as a function of the level detuning. And what you might naively expect is that when the left dot and right dot levels are in resonance, you might expect to see a big elastic peak in the current, right? Because you have kind of a resonant tunneling process. But once you detune away from resonance, you'd expect the current to turn off. And indeed, what they found is if you had a level configuration like this, where an electron would hop from the source onto the left dot, it would actually get stuck in the left dot because there wasn't enough energy to cause it to tunnel uphill in energy at low temperature. So the current was 0. For this configuration, there's elastic tunneling, gives you a large peak in the current. But what they found is that if they went beyond this condition and pulled this right dot level down further and further out of resonance, the current didn't turn off. It persisted. And so they called this long inelastic current tail. They attributed that to spontaneous emission of phonons. Comes back to our charge relaxation from the last lecture. When I have a transition from an excited charge state to a ground state, I need to conserve energy. And in these systems, that happens by emitting a phonon. And so you can see that there are actually little wiggles in the current if you look closely, and the spacing of those wiggles is consistent with the acoustic phonon mode in the system. Another experiment that they did, someone was asking about this during the break, can you actually do coherent experiments with charge? They did a very powerful experiment using a pump probe technique where they measured the lifetime of an orbital excited state. They prepared the quantum dot in an orbital excited state. They measured the rate at which it relaxed to the ground state, and the time that they extracted for that relaxation process was about 10 nanoseconds, or 100 megahertz kind of rate. Again, consistent with electron-phonon coupling. And therefore, if you look back, late 90s, early 2000s, the prevailing notion was that if you had inelastic tunneling in a device like this, you would just generate heat. It would just heat up. There's no light. But now we have a device where, in addition to the electron-phonon coupling, we have this coherent electric dipole coupling between the double dot and the cavity. And this is what's new. And so what I want to explore now is whether or not in these cavity-coupled devices, we can actually get light out. So here's a simple measurement. It's a double dot. It's in a cavity, same system as before. And we're going to force a current to flow through it. Here's a plot of the current as a function of the right gate voltage and left gate voltage. You can see that there's a non-zero current in these so-called finite bias triangles. And what we did in this experiment was just hook the cavity output up to a spectrum analyzer. And we measured the power spectral density of the radiation emitted from this cavity, and you can actually see a small photon emission rate. But these experiments by Yin Liu showed that we'd actually get light out of this device through a single electron tunneling process. And so when an electron tunnels from the left dot to the right dot, every 1,000 or so tunneling events, you get 1 photon out. And that signal was just above the background noise of our amplifier. What's kind of more interesting is we can do a different measurement. We can shine light into the cavity and see if it gets amplified by this device in some kind of way. And that's what's investigated in this slide. This is the power gain as a function of right gate voltage and left gate voltage. And you can see that power gain is largely 1 in most regions here. The double dot's really not doing anything in most regions of space, but there are what we call hot spots in this paper where there's a huge gain. You shine light in, and the power of the light coming out is a factor of 15 higher. So somehow there's an amplification process that's taking place due to the current flow through our device. Another thing we notice is if we measure the transmission through the cavity, in Coulomb blockade, there was a Lorentzian with a Q of about 4,000. But if we move to one of these hotspots, we saw a big power gain, but also a pretty substantial narrowing of the cavity line width. Okay? So the mechanism for what we think is going on here is that if you want to make an amplifier, you need to be able to dump energy into this photonic mode. So we need a 2-level transition that couples to the cavity, and we need a way of populating the excited state. And the way that this happens in the double dot is through 2 sequential single electron tunneling events. Start in the ground state. There's a tunneling event associated with the left dot. We move that electron over to the right dot, and that brings us back up into the excited state. Okay. It might be easier to see from this picture, but we load electrons into the left dot. Now we have population inversion. Right? There's only 1 electron in the system. That electron tunnels downhill in energy, it emits a photon and leaks out of the right dot. Now the double dot's empty. Where does the next electron come from? It comes from over here and repopulates the excited state. And therefore, it's this sequential tunneling process that preferentially loads this excited state and gives us the population inversion that we need for stimulated emission. Okay. You can think a little bit about the performance of the device and where we're at in cavity QED in terms of quantity that's called the cooperativity. And the cooperativity of a quantum optical device in cavity QED, you can think of it as the ratio of the good couplings in the experiment to the bad couplings. The good coupling in our experiment is the coherent electric dipole coupling between the charge and the double dot in the photonic field of cavity. We want that interaction rate to be fast. Fast compared to what? Well, compared to the bad coupling rates. And unfortunately, the bad coupling rates come in two different forms. Our cavity is not perfect, and light leaks out, right? The mirrors are not perfect. There's a cavity decay rate, and that's called kappa, and there's a qubit decay rate. There's a lifetime, finite lifetime of our qubit, and that rate is gamma. And so in general, we want g squared over kappa gamma to be big. But if you plug in parameters for our device, you see that it's less than 1. So we're kind of below threshold in terms of achieving stimulated emission. And I put this kind of famous quote here from Arthur Shallow. He was a famous scientist who worked on lasers and masers, and he has this quotation, anything will laze if you hit it hard enough. And I went back, I don't know, do you know him, Phil?
Oh, yeah, very well.
Yeah. They have a paper in an obscure journal where they try to get Jell-O to laze, the Jell-O that you can eat. But they were trying to show that indeed anything will laze. You can try this with your neighbor and hit your neighbor and see if your neighbor lazes. There's some limitations to the statement, right? But we're curious, can we actually get these sort of single electron devices to laze or maze? And physically, we want this to be greater than 1. And you can try to make G bigger, you can try to make better cavities or better qubits. And we took a brute force approach based on the inspiration from this quote and made a device, it's called the double-double. And what the double-double is, it's not a McDonald's hamburger. It's a device where we have a cavity and it has 2 double dots in it. And the idea is that by having 2 emitters in the same cavity, we're just gonna double the pumping rate and try to get a cooperativity that's greater than 1. That's the basic idea. And here's an EU again by her setup. This is what the device looks like. It's a cavity with 2 double dots in it. And remember, these dots are controlled by gate voltages. And the gate voltages on the left dot and right dot can be independently tuned. So we can turn each one on and off and kind of look at interactions between this. This is kind of intriguing. What we did is we shined a small field into the cavity and we measured the transmission. Shine light in, see how much comes out. And we're just plotting the ratio here as the output power divided by the input power as a function of frequency. Now, take a look at this truth table. This shows the configuration of the double dots. Off, off means no current in the left double dot, no current in the right double dot. And we just see a Lorentzian in the transmission consistent with the quality factor of a few thousand. But what you found is that if we turned on the left double quantum dot such that there was a current flowing through it, that puts us here for the blue curve, that there was a gain by about a factor of 10 in power. So you shine, a milliwatt in, you get 10 milliwatts out. We could reverse the roles and turn the right double dot on, but turn the left emitter off. And again, we saw a gain of order of fraction of 10. But when we had a current flowing through both of them, there's a huge enhancement in the power gain. Now we're shining light in, and we get 1,000 times more power out. Single electron tunneling events are really, doing something inside the cavity that are amplifying the light field. This kind of smells like a laser maser. To further investigate this, we can just take a spectrum analyzer and hook it up to the cavity with no field pumping the cavity. We just have current through both of the double dots and measure with a spectrum analyzer what's coming out of the cavity. And here are the results. This is the power spectral density of the radiation emitted from the cavity as a function of frequency. And we see that there's a peak in the emission. It has a line width of about 34 kilohertz. That corresponds to a coherence time of about 10 microseconds, or a coherence length that's on the order of a few kilometers. Okay. So we see amazing with a long coherence length. Question is, how good is that? It sounds like a pretty impressive number, 3-kilometer coherence length, but is it good enough? One way to quantitatively stack up the performance of the device is by comparing to what's called the shallow Towns limit. And what shallow Towns considered is a competition between stimulated emission events, which all add up coherently to give you a large phasor field, and spontaneous emission events that randomly occur and basically kick around this phasor in this electric field plane. And you can kind of see from this picture that, all right, these spontaneous emission events are going to kick the phasor around, but if I have a massive, stimulated emission field to begin with, then one photon on top of that doesn't do a whole lot. And the shallow Towns prediction basically says that the line width should go like 1 over the output power of your maser. And if you plug in parameters for our device, we expect a line width that's about 400 hertz. And we're about a factor of 100 off of that. The real test to see if this thing is a maser or a thermal source is to actually measure the statistics of the output field. And this is a phasor diagram. Imagine I have an electric field that has an amplitude and a phase. For a thermal source, if you were to look at a histogram of the phasors, measure the electric field as a function of time, and plot how the field amplitude and phase evolve. For a thermal source, you'd have random phases and fluctuations in the amplitude. For a stable oscillator, you'd have a phasor with some amplitude that's fixed, and it would just process around on the plane with the e to the minus I omega t dependence, right? And you just have a circle in the phasor plot. And therefore, this is what you'd expect to see for a stable oscillator. Phasor would just process around in the complex plane, whereas for a thermal source, you see a distribution of amplitude and phase. And we set out to measure this. The hard part of this is really just technical. If you have, say, a nitrogen vacancy center, and you want to measure correlation function for the light, you can buy off-the-shelf single photon detectors, and it turns into a fairly straightforward kind of experiment because you just buy little detectors that click every time they see a photon. For these devices, the radiation that's emitted is in the gigahertz range of the electromagnetic spectrum, and that only corresponds to an energy that's about 30 microeV. And if you just take a standard amplifier and try to measure this radiation, your signal will just be swamped by the background noise of the amplifier. And there's been a lot of work in the field by Andreas Walrath, Michel Devereux, and others trying to figure out how to measure correlation functions of light in the microwave frequency range of the spectrum. And we benefit a lot from having Christopher Eichler join our group for about a year, and he taught us how to measure these correlation functions. I'll show you the data now. These are what we call IQ histograms of the field that's emitted from this device. And the upper plot shows you what the histogram looks like below threshold. The lower plot shows you what it looks like above threshold. Let me explain how these data are taken, right? The device is emitting light. We sample it for about a second. We measure the electromagnetic field for about a second. And for each microsecond interval of that 1 second, we extract the amplitude and the phase of the output field. That's 1 point in a plot like this. We end up with 1 million points, and that gives us a data set for our histogram. And so you can see that below threshold, there's a large amount of counts in the histogram that have amplitudes close to 0 and randomly distributed phase. This is consistent with a thermal source. And if we look at the statistics of this histogram, it's consistent with a thermal source that has a temperature of just about 4 Kelvin. In comparison, if we drive a current through both of the double dots, notice 2 things. First is that qualitatively the plot looks very different. Instead of having a peak at 0, we now have a donut-shaped histogram. But also, if you look more closely, you'll see that the amplitude has changed by about a factor of 10. We're getting much more light out. The intercavity photon number is much higher, and it also has a qualitatively different kind of character. And so looking at this picture from Siegmund's book, right, this is what you expect for a maser. This is what you expect for a thermal source. And you can see that we can actually drive the system across threshold and make a maser that's driven by these one-by-one tunneling events.
Question?
Yeah.
In your measurement, are you like amplify the signal homodyne detection? The previous slide, maybe I think.
Yeah.
Yeah. Do you amplify your signal by D input?
What we do is we take the cavity field
Yes.
and it goes into a low temperature superconducting, it's called a parametric amplifier.
Okay.
And the parametric amplifier has a very low background noise. It
I see.
has a background noise level that's on the order of 30 photons. Okay, and the best you can do is 1 by quantum mechanics, right? So it's not too far off of the limits set by quantum mechanics. Let me put that in comparison with like the first measurement we did. You can see that the background photon rate from the amplifier in these data was 30 megahertz. And we pushed that down to 30 photons per second, kind of using the superconducting amplifiers. There are some technical details about how to measure these correlation functions. If you're interested, we could talk afterwards. It's a little heavy, experimentally, because you need to analyze the data kind of in real time using FPGAs and other things. But it's been worked out and it's kind of routine in the lab now, but it took a couple of years to figure out how to do it. All right. Just want to point out, there have been related experiments looking at photoemission from superconducting devices. This is work by Astafiev et al. From 2007, showing that they could take a Cooper pair box and voltage bias it and see photoemission. It's also from Max Hofheinz, a group in France, showing that they could take a Josephson junction and couple it to a cavity in the low quality factor limit and see photoemission. Right? So a variety of both semiconductor and superconductor devices are capable of emitting light. One of the things that sort of separates our system from the superconducting system is that we have strong coupling of phonons. There's this electron-phonon coupling that gives us another channel that we can dump energy into. There's also charge noise in our system. The charge noise causes the energy levels of our quantum dot to fluctuate as a function of time. When you think of atomic system, you think of something typically it's extremely clean, and you have some transition energy, and that's not changing by much. But these energy levels in our device are set by gate voltages, and any noise in our device acts like a gate voltage, and it causes these levels to fluctuate. And you can see a direct manifestation of those fluctuations here, where this device will emit radiation, and then it blinks off for some period of time and then turns back on. And we think these are due to charging events that kind of take the system out of resonance. In terms of the phonons, another surprising thing about this device is that naively we expected to see strong coupling between the double dot and the cavity when they were in resonance. What we found experimentally was pretty extreme, is that we could detune our artificial molecule transition many times out of resonance with the cavity and still have efficient coupling of light into the cavity. And the theory of this has been worked out by Michael Goulans, but you can have second order processes in this device where you have some transition energy in your system. Part of the energy is dumped into cavity photon, and the rest of the energy is conserved by spontaneous emission of a phonon. And there are these higher order events that turn out to be very significant in this device in terms of the photoemission.
So the asymmetry of the phonon-like profile is due to the continuous spectrum of phonon, isn't it? Qualitatively.
There are a couple of things that matter. So one is the coupling rate between the double dot and the cavity, the G
Yes.
dipole moment, is strongly detuning dependent. If it's far detuned, the G goes to 0. If it's at 0 detuning, the G is maximum. The other thing that you care about is the population inversion.
Yes.
The population inversion is not so high here because there's a strong admixture of the charge states. So you end up with molecular bonding, anti-bonding states. And so if you actually increase the detuning, you'll get more population inversion. So these things go in opposite ways. Detuning is good for population inversion, but it's bad for dipole coupling. What the phonons do is they kind of relax the constraint in some sense, because instead of just thinking about electric dipole coupling, you can have electric dipole coupling plus electron-phonon coupling that gives you a channel for energy relaxation at high detunings. And what Michael did is he carefully looked at the competition between these three factors, the G, the population inversion, and sort of worked out all the details of this phonon coupling mechanism. The details are in this paper here. The early predictions about 4 years before this work, predicted that the width of this gain feature would be set by the cavity line width, which is just a few megahertz. And we find something that's much, much broader than that, 25 gigahertz. And the only way to really explain it that we know of right now is through this phonon mechanism. I think I'll skip over this just in the interest of time, but you can take this device and clean it up quite a bit using a process called injection locking. And what this does is it kind of uses a seed tone to give you stimulated emission and results in a much narrower line width. This is more recent work where we've kind of asked a question, can we take this quantum dot light source and use it to read out other qubits in an experiment? And generally, Steve can tell you and others, you try to buy a microwave source, they're quite expensive. And so it's a question of, can you make a microwave source on the chip at low temperatures that you could use to read out the qubits in your experiment? This is recent work from Yin Yu Liu, where we showed that we could take a device, generate photons, make a maser, and then use the light generated by this double dot to actually read out a second double dot that's in the same cavity. So you can imagine you have light, it's generated, and you're going to use that to image the other double dot. What we can do is measure the power spectral density of the radiation emitted by this device as a function of frequency, and can do this for the target double dot configured in a few different cases. If it's in Coulomb blockade, we see a sharp emission peak. If we move to an interdot charge transition, the coupling between the charge dynamics and this double dot and the maser results in a little bit of a frequency shift. If you look at the blue curve, it's shifted by just a little bit relative to the red one. But if we move to a transition associated with a lead transition where the total electron number in this double dot changes, you can actually see that the power goes down by quite a bit and the peak's a lot broader. And so what you showed is that we could measure the power emitted by this device over a narrow bandwidth and use that to kind of nicely map out the stability diagram of the other double quantum dot that's in the cavity. And what's interesting about this kind of in the long run is that this device works at 8 millikelvin in the same cavity as our qubit. It's generating the microwave field that we want to use for readout, and it could possibly simplify the experimental complexity quite a bit because it's just a DC biased double dot that is acting like a microwave source. It's kind of an interesting way to think about readout moving forward. Yes?
Why does there seem to be symmetry between the right and left intensities?
Yeah, you can see that depending on whether or not you're looking at a left dot charge transition or a right dot charge transition, there's a different signal level. And the reason for that is we're not doing direct charge detection. What we're measuring is the polarizability of this double quantum dot. And that affected polarizability is going to depend on the ratio of the frequency at which we drive to the tonal rates. Let's say that the tonal rate is a hertz, and we try to drive it at a gigahertz. There's just no coupling, right, because they're so far detuned. And therefore, by analyzing the strength of these features, you can actually quantitatively determine what the tonal rates are. So I don't know if that was a clear explanation or not, but you can measure the transitions, and the transition amplitude depends on the gammas, the rates in the problem relative to the drive frequency. And so here, they're nicely matched. But for this right dot transition, if you were to extrapolate between this triple point and this one, you'd expect to see a line, but we don't see a line. And that's because this rate is too slow. But as we go to more positive voltages, that rate becomes larger. And over here, you can see it. Okay. And so this can be viewed as a strength or weakness. It's a strength in the sense that it gives us more information. With just the basic charge detection, I can tell you whether or not a charge transition took place, but it's hard for me to assign a rate to that charge transition. With the cavity measurements, you can determine if there was a transition and determine the rate, the tonal rate associated with that transition. It requires some analysis though, right? Any other questions? Okay, so I'll just try to wrap up here in a few minutes and talk about what we've been trying to do. So I showed you that by driving a current through the device, we get light out, can make a maser, can measure the statistics of that. We can use that radiation to read out other devices. But what really got us interested in this field is this proposal from Daniel Loss's group that you might actually be able to couple spin qubits that are placed inside of a microwave frequency cavity by using a single photon. And for this to work, you want to be in a regime that's called the strong coupling regime. You want the coherent coupling rate between your qubit and the microwave photon to be much greater than all the loss rates. You have a cavity loss rate and you have a qubit loss rate. And we discussed this in the previous lecture. For charge, the dephasing rates and relaxation rates are pretty fast. So you have gammas, qubit decay rates that are between hundreds of megahertz and a gigahertz. It's really difficult to reach strong coupling regime because this incoherent loss rate exceeds by a couple of orders of magnitude the good coupling rate that you want. So you really want this to be much bigger than this and this. For amazing, it's a less stringent constraint that needs to be met. You just want the cooperativity to be greater than 1. But here, G needs to be bigger than both kappa and gamma, not the product of kappa and gamma, okay? And what this means for us is that we needed to develop a better qubit. And more recent devices here, this is a paper from earlier this year that just kind of outlines the technical details. Instead of working with the nanowire devices, we've made a transition to circuit QED samples that are made from a silicon-germanium quantum well. And it looks pretty similar to our indium arsenide device, except kind of the heart of it is now a silicon double quantum dot that's made using these overlapping gates. To make the cavity perform better and have a smaller cavity loss rate, kind of scrutinize this picture, you can see that these patterns up here look a little bit different. And what we've made are little low-pass filters. On all the wires that run into our device, we put a low-pass filter in series. And the purpose of these low-pass filters is to prevent the microwave frequency photons in the cavity from leaking out of all these quantum dot gate lines. It's different from, say, maybe Andrew Houck's talks where you just have a transmon qubit that's capacitively coupled and there's no DC wiring going in. In our devices, we need to bias up these gates. We need to get a DC voltage in all these gates, and every wire that runs into the cavity is a pathway for microwaves to escape from. Right, that's a problem. And what we do is we make low-pass filters. They're like chokes. They prevent microwave frequency radiation from leaking out of the cavity, and it gives us a higher quality factor cavity. Now what we can do is directly measure the double dot charge stability diagram. What's plotted here is the cavity transmission as a function of the right gate voltage and left gate voltage. And now I hope you can really see, with your naked eyes, this is a charge stability diagram. This is a right dot charge transition. This is a left dot charge transition. And there's an interdot charge transition. There were a lot of questions about absolute electron number. And how do you know that you have 0 and not 10 or 100? And here I hope you can see it. We see charge transitions, but then there's nothing in the right dot. We see charge transitions, 1, 2, 3, and then there's nothing in the left dot. And that's how we assign 0, 0, empty, empty to this configuration. Is that okay now? You can kind of see it, directly in these cavity measurements. Now what we can do is we can zoom in on an interdot charge transitions, the red circled one here, and kind of take a closer look at how the device performs. This is a plot of the transmission through the cavity. We can measure the cavity loss rate. It's about a megahertz. This is the qubit transition frequency. We can measure the line width of our charge transition in this device. It's about 5 megahertz. And the question is it good enough? We have 1 megahertz photon loss rate, a 5 megahertz qubit loss rate. How does that compare to the charge cavity coupling rate? What's shown here is the cavity transmission plotted as a function of frequency. And this axis here is our detuning. Remember, the detuning is just the energy level splitting in the double dot. 0 detuning means, left dot in resonance with the right dot. And what you can see from these data is that when we lower the qubit transition frequency and bring it close to the cavity frequency, there's a void crossing. There's actually hybridization between the cavity mode, the photonic mode of this cavity, and the charge state of the double quantum dot. And we have this void crossing. You can take line cuts through this data, and what you can see is if you take a cut way out here, the qubit is off resonance with the photon and nothing really happens. You measure the transmission through the cavity and it's just Lorentzian. But when the qubit is brought into resonance with the cavity, light and matter hybridize, and you end up with this so-called vacuum-Rabi splitting. And in this paper, Mi was able to show that we could reach a condition in our silicon devices where the coherent coupling rate actually exceeded all the bad loss rates, the photonic loss rate and the qubit loss rate. And what this means now is that we can kind of head in a direction where we can start to couple our silicon qubits using a single microwave frequency photon. All right. Just kind of finish by talking about these measurements. The circuit QED approach is also helpful for measuring the energy level spectrum of our device. And silicon has a potential complication in that its band structure has what's called a valley degeneracy. But if we look at the gallium arsenide system, all the electrons in gallium arsenide sit at the center of the first Brillouin zone called the gamma point. But in silicon, there are 6 equivalent pockets that the electrons sit in that are about 0.85 times out to the edge of the first Brillouin zone. These are called valleys. And there's a question of whether or not this degenerate 6-fold sort of valley state spectrum can be split off so that we just have one valley that's occupied with the electrons. Let me explain why this is important. If we want to make a qubit, we just want to have spin up and spin down as our basis states, just a simple 2-level system. And this is what happens in gallium arsenide, where you just have one electron in no valley physics. You apply external magnetic field, you have Zeeman splitting, it gives you an energy difference between spin up and spin down. In silicon, if we have another low-lying valley state, we'll have Zeeman splitting of the lowest valley state and some excited valley state, which I'm showing here in blue. And that excited valley state will also have Zeeman splitting. And you can see if this valley splitting is small, we can actually have thermal mixing of the spin down states in the ground state valley and in the excited state valley. And therefore, instead of having a nice clean 2-level system with just spin up and spin down, we can have spin up and spin down in the ground state valley and spin up and spin down in the excited state valley. And if those are mixed, it's a problem because a valley degree of freedom is an orbital degree of freedom. And it's not clear how long-lived it is and how coherent it is, right? So the approach right now is do whatever you can to get that valley out of the way so that you only have one, right, in the ground state. And the first step for us is to come up with a way to actually measure the valley splitting in these devices with one electron. And the way that we're doing this is by using cavity QED. Here's a picture of our device. We have a double dot, and silicon has a ground state in the left dot, a ground state in the right dot. And now we've included a potential complication that there might be an excited valley state in the left dot and an excited valley state in the right dot. And that gives us a 4x4 Hamiltonian that we can plug into cavity input-output theory and make a prediction for what the cavity transmission should be. And what we can see is that if there's a valley state, a low-lying valley state, instead of seeing one peak in the cavity transmission, we'll have sidebands that are associated with avoided crossings linked up to these excited states. It's pretty cool as they really pop out in the data. You can measure the cavity transmission as a function of right gate voltage and left gate voltage. And we see the interdot charge transition before, as we did in indium arsenide, but now it's accompanied by these faint sidebands. And these sidebands are associated with these avoided crossings in this energy level diagram between a ground state level in one dot and an excited valley state in the other dot. Okay. We can increase the visibility of these valley features by just turning up the temperature. At low temperatures, all the population is in the ground state and we only see the ground state transition. But if we increase the temperature, we'll have some thermal population of these excited states and they show up more clearly, just basically by a Boltzmann factor partition function. Can also hook the device up to a battery and force electrons to flow through this double well system. And what that means is instead of having all the population in the ground state, we can load population into these excited states. And what we measure is the time averaged occupation and the response of the device to the cavity field. And you can see there that under the influence of applied source parent bias, we can also increase the visibility of these valley states. Now we have a nice way of actually probing valley degree of freedom in a single electron device. And this has been hard to get to using conventional transport approaches. All right, what do we think could be impacting valley splitting? Well, it's known that increasing the electric field is good for valley splitting. It's known that interface abruptness is a problem, interface roughness is a problem. And we've therefore began to look a little bit deeper at the materials physics associated with our devices. This is a silicon quantum well, and you can see the gate electrodes that we use to make our device on top of it. And we're curious, you know, how clean is this interface, the silicon quantum well? This is work with Donovan Leonard and Andre Dyke at Oak Ridge National Laboratories, and they've been doing high resolution transmission microscopy to measure the interface abruptness between the silicon quantum well and the silicon germanium spacer layers. And we see that in contrast to, say, gallium arsenide, where you can really have an atomically abrupt interface between gallium arsenide and aluminum gallium arsenide, this is a fairly broad interface. And that reduces the potential step between the silicon quantum well and silicon germanium, and can also be partly responsible for small valley splitting. And therefore, you know, moving forward, we'll be paying more attention to the material's growth properties. Let me finish up with this. I hope I talked to you a little bit about spin qubits and, you know, what we're thinking about now in terms of coupling charge delay. Thanks for your attention. Any questions? I had a few during the lecture, but there are more.
Would it be better to have like a phosphorus ion doped into silicon so that we don't have those valley degree of freedom?
Yeah, the question is, instead of making these gate-defined quantum dots in silicon germanium, would be better off using phosphorus doped silicon, or Steve might raise his hand and say silicon MOS. And I have my own strong opinion about donors. I think that donors are really good for single qubits, but they're so small that if you want to have nearest neighbor exchange coupling, then you need control of matter at an atomic scale. And that can only really be done with STM, by building devices from the ground up. Donors are great for single qubits, just like NDs are really good for single qubits, but going beyond single qubits, we need a way that we can lithographically, you know, make things on a meaningful length scale, and that means tens of nanometers. Therefore, I'm down on donors long term. I think they're nice for some things, but I don't see them scaling well. MOS is interesting because you have a large electric field at the silicon-silicon oxide interface. The trade-off is that the mobility is generally much lower, like 10,000 instead of 500,000 is what we have now in our silicon devices. And MOS groups have worked really hard to make nice dots, but it's been challenging to have the control. And maybe that will change with better materials and better processing techniques. But at this stage, they're sort of still at the level of a couple of dots. And we'll see. I'm more optimistic about MOS. And if we needed to make a transition from silicon germanium to MOS, we could do it. We could use the same gate designs. But right now, I like the fact that our devices are buried. The electrons are at an interface that's 50 or 60 nanometers below the surface. It's clean. The mobility is high. And we have good control of it. The downside is valleys, you know, and the valley splitting is 50 microeV. If it were 100 or 200 microeV, it would be big enough that we wouldn't care about it. And my hope is that we'll get it there, but you know, there's more materials work that's required to do that reliably. Any other questions in the back?
So I've seen a couple of papers using some of these microwave photon to atomic or spin qubit couplers, essentially claiming that they're able to use these to do quantum non-demolition measurements on the photon. And so I was wondering after that if these things would potentially be a realistic implementation of quantum non-demolition measurements in photonic circuits, which would probably relieve a lot of the things that have basically been holding quantum optics back for the last 5 to 10 years, from what I can tell.
Mhm. Yeah, so for qubit coupling the photons, you generally want to work in a resonant regime where the qubit transition energy is matched to the photon frequency. That way you can do a direct swap between your qubit and the cavity photon. For readout and for QND measurements in these kinds of systems, generally the measurements are performed in what's called a dispersive regime. You have your photon energy, but you detune your qubit transition energy by a few cavity line widths so that they're no longer in resonance. And what this does, I think I had the Hamiltonian in one of these slides. It gives you it's called a dispersive shift in the field, but you can measure a shift in the cavity transmission frequency. Normally you think h bar omega, and omega is set by the cavity, the L's and C's in our circuit that basically set up the resonator. Let me see if I can find it here. This is the equation I'm thinking about. This is the Jaynes-Cummings Hamiltonian written down in the dispersive limit. Just walk through the Hamiltonian. There's light in the cavity, and the energy is h bar omega a dagger a, set by the number of photons. In the dispersive regime, you see that the photon energy can be conditioned by the state of the qubit, sigma z. And the amount of the dispersive shift goes like g squared, this coherent electric dipole coupling, divided by delta, the atom cavity detuning. And therefore, the photon energy is dependent on the state of the qubit. This is the key ingredient for QND. We can use photon measurements to perform a non-demolition measurement of a qubit, but I think what you're suggesting is beyond that. You want to do a QND measurement on light, right?
Yeah.
That's what you're suggesting. And I think the only thing that comes close to that is there's recent work by the Yale group where they're using what's called a Kerr nonlinearity to have nonlinear effects in cavity QED implementations. And they're using sort of cat states of light to make qubits instead of physical qubits based on superconducting qubits. And I'm not sure if they can do exactly what you're suggesting, but it's definitely closer than it was a few years ago. Yeah, you can sort of see nonlinearities in the cavity response that are due to a qubit. The qubit kind of adds a nonlinearity to a normally perfectly harmonic kind of oscillator system. And that's where that's headed. Any other questions? I think there was one up front, yes.
How many values do you have on the surface?
Yeah, okay. Valley physics. The picture I showed here is the first Brillouin zone of bulk silicon, which has a 6-fold valley degeneracy. Now, that's what this picture is. Now, what we do to make our devices is we don't work with bulk silicon. We work with a 2-dimensional electron gas. And this 2-dimensional electron gas is grown in a special way in that the silicon quantum well is grown on top of silicon germanium. And germanium has a lattice constant that's just 4% bigger than silicon. And what that does is it stretches the silicon out. It puts the silicon under tensile strain, and it increases the in-plane lattice constant, and it slightly decreases the out-of-plane lattice constant. And that pushes 4 valleys up in energy and leaves you with 2 plus and minus z valleys. And what we're interested in is what's happening with those lowest lying valleys, because these other ones are a couple hundred MeV out of the way, just big energy for our system, right, at low temperatures. And really, it's that physics of what happens to these 2 valleys that we're intensely interested in, put it that way. Any other questions? All right, well, thank you. Hope you enjoy the lectures, and lunch is waiting for us. Thank you. Thank you. They claim that they made some progress on it, and they sent us new wafers.
Are they doing it with CBD or are they doing it with the sort of order would be that MBE might be better. And I had been thinking, Chef Yeah.
You know, there's Peter Gilman here
Yeah.
at HRL, and then
换
we
一
have
下
a
就
new
好，你觉得
team member
哦，
who's
我
just doing CDD.
So
This
it
very
goes
nice.
sort of out of the.
那
I haven't heard
对
from that.
那我如果换成后的话是，比如说后的质量是比 electron 我知道是大5倍，是我整个成
He
本
was, he came out of
我觉得应该不是吧？
the same group at Caltech that Andy Hunter
I
and
see.
I had,
也可以
though
变成
we didn't over.
但是但是你说出来就不是基本就说
He was a ginger. I used to be
就是整个这个乘以5还是
I
关
used to be able to go in the lab.
就不知道，拿去
Now I
拿
just
去
I only people who to the bathroom.
可能有一个
Is that right? Everything is very
It's sort of
locked
locked
down.
Yeah.
这不是后
It's
下
the
面这
nature of
个
our field, unfortunately.
Hmm?
This is the nature of the field.
Yeah, I'm getting a little
但
concerned about all that.
没有后
Yeah.
Maybe I'll,
你简单
maybe tell me it's time to retire.
Yeah. I'm starting a company.
它应该不是一个简单病，我说它5的按照一直是一条整病。
Computer probably is plugging in, so I can just go ahead and look at it.
We got some good stuff on the way. What happened with your ARO stuff? Did you get part of the
Well-
call, or what are you not doing?
Well, so I have decided that I'm gonna get out of silicon. I figure silicon is, well, yeah, silicon's turning the way HRL is, right?
Yeah.
And it's into that kind of stuff. And so what I'm gonna do is just do the electrons on helium business.
Okay.
I think, well, it's a scheme where I think we can have a lot more impact, only that, it's not as crowded.
Mhm.
I also think in the long run it has a lot better prospects, but that's open to debate. But yeah, they had this